Hi, y'all. This selected solutions video is going to be a tad different than the others, just because I'm going to answer 3 questions all in the same video. It's 3 consecutive questions because this assignment, the initial rates assignment, is not randomizing your questions because a lot of the questions refer to the same table again and again. So you should be on question 8, 9, and 10 unless there's something weird going on. So what you'll want to do to best benefit this video is to make sure you've got this pulled up, because in a moment I'm going to be pulling the data away from the screen and you won't know what I'm talking about. So make sure, because I'm not going to draw the table, so make sure that you've got this in front of you. Okay, so one of the reasons that this problem confuses you is if you look at the equation up here that we're starting with, there's only one reactant. So in the lecture examples, we were always dealing with more than one reactant that would have individual kinetics that we needed to investigate. However, since this reaction only consists of a singular reactant, then there's no comparison to make between kinetics. In other words, the NOCl is going to drive all the kinetics on its own. So you'll notice that in our table, we don't have to do that thing where you say, okay, well, this reactant stayed the same in these 2 trials, so I can investigate this reactant in the same 2 trials. We don't have to do that. We can just pick any trials we want and do a comparison, all right, to find the power connection, just like we did in class. Now, you could just use trial 1 and trial 2 and go through, divide the bigger number by the smaller number, blah, 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 and we're going to go through that in a moment. But I'm not going to use 1 and 2. The reason I'm not is because I can see right away that if I divide 3E16 by 2E16, it's going to give me a decimal number. It's fine. You can do it. You can use the decimal number. It just makes the power investigation a little more annoying. But look what happens if I use trial 2 and 3. It looks like the numbers are going to be a lot friendlier to me if I do that. So again, you can pick any 2 trials you want, and you're going to get the same rate law, the same everything. But I am going to pick trial 2 and 3 just because I can see that the numbers are friendlier. All right, so trial 2 and 3, as you can see on the page there. So we're going to do what we always do. We're going to divide the bigger number by the smaller number. All right, so I'm going to start by going 2.0 E16 divided by 1.0 E16. Those are the 2 trials that I'm looking at, and I'm going to get the number 2. I'm going to divide the same trials again, but using the rates that they give me, which is 2.66 E4 over 6.64 E3. And that gives me the number 4. Now remember what we're doing here. In order to find the order of this reactant, which happens to be the only reactant, I want to know 2, or this value, to the power of what equals that value. All right? So in order to make the 2 become a 4, it would be a 2. 2 to the power of 2 is 4. So now I can easily write the rate law. All right? I'll go rate equals K, and that'll be of the NOCl, all right? Not only is that the reactant that we are looking at, it's the only reactant, and it has an order of 2. So that's one of the questions. The next question that it asks is, what is the value of the rate constant? All right, well, to find that, we very simply need to plug and chug, right? The rate constant, remember, is K, all right? K is the constant. So that's what we're going to be calculating here. So if you remember in class, now this was something I said to always do. When solving for K, you always use trial 1 because that's what the graders are going to have. So let's prepare to plug and chug the data, and again, make sure you're looking at the table. If I pulled the information from 1, it's got a rate of 5.98 E4, And now I'm just plugging into this rate law equals K. Now I need the concentration of NOCl there, which is 3.0 E16. And then make sure you don't ignore the order. All right, so if we start to simplify, it'll come out to 5.98 E4. All right, I need to square this number, and it comes out to K 9.0 E32. So we would divide by 9.0 E32 on both sides in order to get a final K value. And in this case, I end up with this value here. Lastly, there is a third question, and this one is way different. It's an application question that I know is one of the biggest struggles in the whole assignment. So it's question 10, I believe, and it wants you to do a conversion. It says calculate the value of the rate constant when the concentrations are given in moles per liter. So it wants you to use this number, all right? But it wants you to convert the units, which I know can be a little annoying. So watch closely because it's definitely something that you've had practice doing. So I'm going to take my given value here, all right, of 6.6 E negative 29. And look, that's centimeters per molecules. It's this many centimeters cubed for every one molecule. All right, because remember, remember that line right there in the units is this line right here in the dimensional analysis, right? But now it says, well, that's not the units that we want it in. We want it based on being second order, of course. Remember, we're second order, so we already know what units second order should be in because I've told you to memorize it. But we know that we want units of liters per moles seconds. So that's what the answer should be in. So we very simply just need to fill in all of our conversion factors in order to get there. So let's do some simple conversions. We don't want centimeters cubed. We want liters. So we can go directly from centimeters cubed to liters. All right. Now, a little bit of info that you may or may not know, that centimeters cubed is the same thing as milliliters. So that's something that is just handy math knowledge. Therefore, I know that since there's 1,000 milliliters in a liter, there's also 1,000 centimeters cubed in a liter. So as I bring down these units and I say, okay, well, these need to be equal to each other, I know that 1 liter is the same thing as 1,000 centimeters cubed. And voila, I now have liters where I want them. But we don't want molecules, so let's get rid of molecules. So I'm going to put him up here. All right, now since molecules is on bottom and top, we know the dimensional analysis will eliminate it. And what do I want? Well, look, I want moles. All right, you know this conversion factor. For molecules, it's Avogadro, 6.02 E23 is present in 1 mole. So now if we go through our basic dimensional analysis process here, centimeters cubed and centimeters cubed, molecules and molecules, by running the grid, you'll end up with liters over moles, just like is required by a second order reaction. And when I run it, I get this answer here, 4.0 E negative.